Hello, this is Mrs. Scarple, and in this video I'm going to take you through simplifying radical expressions. So using the properties of radical expressions to simplify. First, I just want to review these properties. If you have the nth root of a to the n, it's going to equal a. So if we just put some numbers on this, let's say I had the cubed root of a to the cubed. Because the index of my root matches my power, my exponent, this is going to equal a. This next property, the nth root of a product of ab, works like that power of a product with the exponents. If I have the nth root of a times b, I can separate that as the nth root of a times the nth root of b. So if I had the fourth root of a times b, that would equal the fourth root of a times the fourth root of b. And c, we have the nth root of a quotient. Again, that's like taking a power of a quotient, and we can separate the numerator from the denominator, each with their own nth root. So if we have the square root of a, or excuse me, let me go back to the beginning here. If I have the square root of a over b, I can simplify this as the square root of a over the square root of b and simplify each square root separately. I also want to remind you of how rational exponents are written as radicals. So if I have a to the m over n, that's the same as saying the nth root, the denominator is your index of your root, so the nth root of a to the m. Your numerator is the power of your base. It can also be written as the nth root of a to the m power. They will give you the same result. So now let's take this information and let's do some simplifying. Rewrite the radicals. So if I rewrite 18, I know this is a square root because I don't see an index here. When you don't see the index, it is understood to be a 2 for the square root. Because my index is 2, I want to find a number that's squared as one of my factors of 18. Now if you can't remember that, what you can do instead is break down 18 into, you could say, 3 times 6, but 6 can be broken down further. So we have the square root of 3 times 6 is 3 times 2. Now since this is a square root, we're looking for groups of 2. And we have one group of 2 3s. So we can write this as 3, because the square root of 3 squared is going to be 3, times the square root of 2. For the second example, we have the cubed root. So we either want to find a number that is a perfect cube, or find groups of prime factors that are in groups of 3. For this one, I'm going to go ahead and use the cubed number. So if I have the cubed root, I know 8 times 24, or 8 times 3, excuse me, will give me 24. I also know that I can break this up as the cubed root of 8 times the cubed root of 3, because I know that 8 is equal to 2 times 2 times 2. 8 is the same thing as saying 2 cubed. So we have the cubed root of 2 cubed times the cubed root of 3. The cubed root of 2 cubed is 2, cubed root of 3. Now make sure when you're writing these, when you have an index, you're putting it in this little crook of the root symbol, of the radical, I should say. And be careful that you're not writing this coefficient in front inside of that space. Otherwise, you're changing what root, what index you're looking for. And for the third one, we have the fifth root of 64. Well, we could use that we know that 8 is 2 cubed. So I'm going to have my fifth root. If I do 8 times 8, that's going to be 2 cubed times 2 cubed. Well, that's more than I need. I could write this as the fifth root of 2 to the fifth times 2 to the first. 5 plus 1 is the same thing as 3 plus 3. So that I simplify the fifth root of 2 to the fifth, and I have the fifth root of 2. When I find the fifth root of 2 to the fifth, that is 2 times the fifth root of 2. Here we're combining some of our exponents with the numerical coefficients. It's the same process. So in this first example, we have a square root. Keep in mind that that index is a 2 when you don't see one there. So I'm going to break down 20 as 4 times 5. And I'm going to break down my x so that I have an even exponent and the leftover that would get me to 7. The reason I'm going to do that is because when I find the square root of 4 times the square root of 5 times the square root of x to the 6th times the square root of x, I can use a rational exponent to help me simplify this x to the 6th. Hopefully you understand that the square root of 4 is 2, and then we have the square root of 5. Then we're going to have times x to the 6th to the 1/2. 1/2 is that rational exponent that represents the square root. And then we're going to have the square root of x. So I know I have a 2. I know I'm going to have 5 inside the square root. When I take 6 times 1/2, that leaves me with x to the 3rd. So we have 2x to the 3rd times the square root of 5x. Both the 5 and the x are underneath a radical, underneath a square root. We can now combine them back into 1. So 20x to the 7th can be simplified to 2x to the 3rd times the square root of 5x. On the second example, I'm going to simplify my quotient first. So I see that I have the bases of x, both numerator and denominator, but I also have that with the y's. I'm going to simplify those before I start thinking about simplifying my radical. So I'm still going to keep the cubed root of 3 over the entire quotient. 16 will still be in the numerator. When I look at the x's, there's more of them in the denominator, so that's where I will write my x. And it's to the 6th power. There's 6 more in the denominator than there are in the numerator. And when I look at the y's, there's more in the numerator, and there's 3 more of them. Now what's nice about this is that my exponents inside my radical are a multiple of 3. So I don't need to break them down anymore because they are multiples of 3, and when I use the rational exponent of 1/3, these will simplify nicely. What I do want to do is break down the 16 while I am simplifying things. So 16 is the same thing as saying 8 times 2. And we're going to have the cubed root of y cubed. And we're going to have over the cubed root of x to the 6th. We have talked about the cubed root of 8 being 2. So since that's a perfect cube, I need to separate that from the cubed root of 2. We've also talked about the property that when the index matches the exponent, you're left with just the base. And since my index does not match my exponent, I'm going to go ahead and write this using rational exponents. The rational exponent for cubed root, I almost wrote for square root. Cubed root is 1/3. So the cubed root of 8 is 2. We have the y that's no longer under the radicals. We have 2y. Cubed root of 2 over x to the 6 times 1/3, or 1/3 of 6 is 2. So this simplifies to 2y times the cubed root of 2 over x squared. And make sure you have that division bar, that fraction bar, completely underneath the entire numerator. Don't just put it underneath the cubed root of 2 or just the y cubed root of 2. You want to have everything in that numerator above that quotient bar. And this concludes the video on simplifying radical expressions.